I don't think I need to introduce myself. Before I start on actually talking about the performance, I have to set some history straight, because what you learn is all Western propaganda. The computer was invented in 1993 in Soviet Oterzirkersdorf by Nikita Khrushchev. Georg Paul Thumann helped, but he protested because he already knew that computers are shit. Actually, they called it hyperhegel back then. They had to stop the project, it burned too much coal. In 1995, a guy called Pio Grad invented OpenBSD. Georg Paul Thumann was the third developer, and in 1997 he left the group over an argument with Theo and founded NetBSD. Yep. OpenBSD came with IPF as firewall. IPF has a few problems. It's written by an Aussie.
Nothing good from Australia.
What?
Nothing good from Australia.
No. And everything's upside down.
Yeah.
There you go, eat my packet, Phil.
So we successfully forgot about most of the technical issues. I remember one, whenever we went over 8,000 states, the machine became unusable slow.
It's a hash.
Yep, it was fucked. When I switched from IPF, the last IPF install I had, the machine was packed at peak time. When I upgraded to OpenBSD, the first one that came with BF 3.0, well, okay, it crashed, but after we had it fixed, I was at 10% CPU usage, so it's quite faster. So in 2001, the RC played a license game on us, and yeah, we decided to leave the shit. PF was born in just less than a month later. It was committed. Back then, it was mostly an IPF clone. It was faster than IPF from the first day on, and it quickly evolved to be way more powerful than IPF2. And OpenBSD and IPF pretty much always could easily withstand comparing with the other OSs. Like, it was not the fastest, it was not the slowest, so you get the idea. And these days, there's actually a few nice OSs in our group.
There you go, eat my Mbuf.
Who are they?
So, why do we want to tune if we're already that good? Answer, because we can. We want to replace so-called hardware routers, which usually are built just like PCs, except the really, really, really big ones. We want firewalls in more places. And the CPU cycles that we don't need for packet forwarding can use for something else. Crypto, user-led proxies, porn, Hangman. Okay, Hangman is kind of single user, whatever. Before tuning, you really want to understand what you're tuning. If you're randomly pushing buttons, you're being an idiot. So, knobs or for knobs. Or spread. That's your line.
Just use polling.
No polls allowed.
Get out.
Blindly making changes, hoping things will be faster, stupid, don't do it. It's not only likely, or it doesn't only have a chance to make things slower, there's also a high chance you fuck up big time and introduce bugs or similar issues. When you want to understand, when you want to hack on the network stack, want to become a rock star like we are, you have to understand mbufs. You must not hack on the network without understanding mbufs. DLG. So mbufs are pre-allocated buffers. They are 256 bytes on OpenBSD. Traditionally, they were just 128 bytes, and I think on some other OSs they still are. BSD_T. Did they change?
Is it type def now?
Wow, they suffer. They suffer. This also means they can never upgrade PF again. They are fucked. Well, this is not PF dependent though. Yeah, to understand it better, use picture. That's a pool of mbufs. The mbuf header structure is actually pretty straightforward. You have a pointer to the next mbuf in the chain. You have a pointer to the next packet header mbuf. I'll explain the chains in a bit. You have the actual data, the data pointer, sorry, the length, the type, and a few flags. So, mbufs get chained. When you have more data than one mbuf can hold, you just chain another. There's pictures showing it later. There's three kinds of mbufs we care about here. One is holding data itself, one points to external storage, and one, that's the most interesting, is the packet header. This is always the first mbuf in the chain that holds, yeah, well, the packet header, the information about the chain and the packet there. The one holding data is the easiest case and the least common case. That is just the mbuf header followed by the data. External data storage means that the data is not actually put in the mbuf itself, but elsewhere, and the mbuf basically has a pointer to it. In our case, elsewhere is usually an mbuf cluster, and mbuf clusters are just like mbufs, pre-allocated buffers, just bigger. 2K in our case, we actually these days have even bigger ones for jumbo frames, but it doesn't matter. The 2K is chosen so that an entire Ethernet frame fits. So since mbuf clusters are bigger, they come from a bigger pool, obviously. This joke is lost on you guys. The packet header mbuf, the most interesting one. As said, it's always the first one in the chain if the chain actually extracts a packet. It contains extra information, the interface we receive the packet on, mbuf tags, like even more tags, checksumming flags, VLAN, and a bit more that it's boring, we're not going to talk about. And the packet header mbuf can even contain data itself or point to external data storage, so you don't need to chain another mbuf just to point to a cluster. So, visualizing that, oh sorry, one slide in between. This is the complete mbuf structure. If you're allowed to tell me, I don't. So, now, pictures. This is easy, everything fits one mbuf. You have the header, followed by the packet header, followed by data. This happens, but it's uncommon. Well, I suppose TCP/X and shit like that can look like that if it's not forward. Anyway, different story.
If it's not IPv6.
If it's not IPv6, yes. Oh, that's what the jumbo clusters are for.
Yeah. It's for the jumbo purposes.
So, an mbuf, the packet header, just like in the last picture, the data area, and it needs more data, so it just chains another mbuf. And the most common case, mbuf with the packet header, and the pointer to external data storage to the cluster, which I'm sorry is way too big to fit the slide.
That picture is wrong. That's wrong.
Why?
Because the cluster has a header.
No, it doesn't.
The cluster doesn't have it. Yeah, well,
No,
picture
that's
that's there.
the problem is the blue in the mbuf.
The area is still there, but it's illegal to use.
Yeah, it's not data. It's just unused.
Unused, whatever, it's still there. There's still a pointer to it, actually. It is there.
No, you cannot point to it.
Yes, you can.
Yes, you can.
Yeah, but then you don't have to then you don't have a cluster anymore. You cannot
Sure.
use the cluster and the data.
Oh, that's right. It's only have a pointer. Yeah.
You can't hack the network stack without understanding mbuf.
Luckily, this is not something to worry about because there's all these lovely macros that help you.
Yes, like the one I discovered today that kind of works on accident and relies on the fact that bcomp aborts early. Lovely. Took DLG and me like 5 minutes to figure out why it doesn't overflow. So, now that you understand mbufs, we'll have to travel. We'll take the very famous packet through the system route. And yeah, some assumptions. Ethernet, IPv4, and no encapsulation in any form. This means no IPv crap, no VLANs, no PPPoE, no IPsec, no GAR-E, no GIF, no other shit.
What about JPEGs?
What?
What about JPEGs?
Jetpacks, not support. So, fasten your seatbelts. Packet travel. A packet is received by the network interface card. This DMAs it into memory. You understand DMA now. You listen to the previous talks. Into the RX ring in the memory that is provided by the driver. That assumes network interfaces built in the century, so we don't look at the PO ones. There were really stupid ones that couldn't do DMA, and well, in the past history there were times where they basically didn't do it. Anyway, So these days, crappy network interface cards still exist, but at least they do DMA. They might do it stupid, but they do it. The RX ring is usually built from Mbuf clusters, and this is the reason why we almost always, at least for not locally originated packets, see an Mbuf pointing to an Mbuf cluster, even for tiny shit like an TCP ACK. We ignore jumbos like the railroad does, and yeah, well, the details on that differ between drivers, so ignore. When that happens, it interrupts to notify the CPU that it actually has to process the packet. And yeah, well, there's another one. We have interrupt mitigation. Ignore. The CPU handles the interrupt sooner or later, depending on the load from other devices and the interrupt priority. The interrupt handler calls back into the registered driver, and so we eventually end up in our NIC driver. The interrupt handler calls either input, and that gets pointers to the interface the packet was received on, and pointer to the Ethernet header, which is not used these days, and the Mbuf from the RX ring. Of course, it's not the Mbuf, but the Mbuf in the cluster. Either input does Ethernet magic, and eventually figures out it's IPv4. It queues our nice little Mbuf in a queue called IP interrupt queue or IP interqueue, and asserts a so-called soft interrupt. When the CPU is done with all the hardware interrupts and basically ready to switch back to user land, it handles soft interrupts. So we end up in a function called ipinter, which dequeues the oldest packet in the ipinter queue and gives it to IPv4 input. In IP input, we do lots of magic that partially we can ignore here. Major point, validate packet, like make sure it's actually long enough for an header to be present before we access the header and stuff like that. Then calls very early on PF test to let PF do its work, check for multicast, IPsec, and all the other boring shit. Figure out whether the packet is actually for us or to be forwarded. This is an astoundingly expensive operation. I have that fixed. Actually, the kernel doesn't boot, but anyway.
Yes.
I have that fixed.
At least it links now. Come on.
Yeah, but it hangs with get because, well, whatever. Done with all that shit, we proceed with local. Oh, sorry. We check whether we're supposed to forward the packet. If it's not for us, and if we forward this, we call IP forward. Note the nice symmetry. IPv4 input calls IP forward, and if it's not to be forwarded, and for us, proceed with local delivery or drop. We're not going to look at the local delivery case. It's hard. IP forward obviously does a route lookup to figure out where the packet has to go to. It handles the ICMP redirect case if it's actually enabled, and it usually isn't anyway. And eventually calls IP output. Should IP output fail, it handles generation of ICMP errors. Wonderful source of slowdown. Of course, to send the ICMP error back, we need some data from the packet that we are dropping or we are applying to. And since IP output consumes that Mbuf, you don't have it at that point anymore. So we need to keep the data somewhere. And we used to do a full Mbuf copy, and this turned out to be a high share of the IP forward cost. DLG fixed that initially, but in a broken way. And then I came and I understood Mbufs. Somewhat. No, and I actually fixed it at this hackathon for real. Well, we don't know whether it's fixed for real yet, it's the break. We'll see when you guys run current. So, IP output is a giant pile of poop with dragons. Fortunately, for the forwarding case, we can ignore most of the steps. And I'll do that. So, what's left? It does the MPU magic. Actually, has to figure out whether the MPU of the interface is big enough for what we are going to send out. It does path MPU discovery, and if required, does the fragmentation. The MPU shit you can ignore. MPU is 1500, period. Everything else doesn't matter. And don't mind about it yourself. It handles multicast, broadcast, IPsec, and all that shit. Doesn't matter in our case. And this is important, finally calls PF test again to the outbound PF check. Eventually, PF doesn't drop the packet and everything went well. IP output calls the interface output routine for the interface in question. No, not directly, it's more complicated, but ignore that. And basically, eventually, the Mbuf ends up on the interface, it sends it out, and some then interrupts to signal completion, all is good. This is more complicated, but ignore that. So, questions so far? You all understand Mbufs now?
Why is it so slow? It's getting bad.
The weather isn't bad, is it?
Sorry.
The weather isn't that bad, is it?
Actually, I have a question for you that hooks into the previous presentation from Marianne. She was presenting a case where you had an 8 gigabyte machine and
Yep.
where you had to sort of restrict the low 4 gigabytes for Mbufs. How much Mbufs are people using on really busy machines? I mean,
Actually, not.
would 4 gigs be a limit for a
Holy shit, that's giant.
Yeah.
If you would store 4 gigabyte worth of network traffic, this is giant latency. Holy shit, no.
So what's a reasonable amount for I don't know, if someone said that you
Highest
cannot
number-
have more than 500 megabytes, would that be bad for you?
I got up to 3,400 Mbufs and then fixed the NFS leak, and now I only use 30.
I still have the NFS leak on mine, I didn't reboot. Yeah.
Well, actually, I get up to 300 now.
Yeah, but it's NFS. We'll leak more again.
Yeah,
it's hundreds to thousands.
I have production core routers to the customer. They're insane. They're doing something like 800 Mbit over them, and there I have seen peaks of 25,000 in the forwarding in the IP interqueue. Well, sorry, 2,500. And so I'll guess the total in the system in that case, which is really high, would be something below 10,000, way below. So 4 gig is more than plenty. You don't want to store it long because you just introduce latency.
But if 4,000 Mbufs is sort of fine or common
The
case,
current
then
limit is over 6,000, so
That's
you
the
could,
default
you
limit.
could
That's the
almost
limit-
have it in the
default
ISO
limit,
space anyhow.
4 gig is wide enough.
Yeah.
for now,
Yes.
It is enough.
Yes.
for now.
You can probably use the memory for other things than the Mbufs too.
Yeah, I have slow slip links I need to.
What for? No. Other stuff doesn't matter.
Nobody's using OpenBSD. How's that not working?
Propaganda. So, performance. Start with low-hanging fruit because otherwise I have to explain even more, and I will do that in a bit. But there's a really easy optimization I did at C2K7 or 8. 8
Just 2 years ago.
7. Just don't recurse into IPsec if IPsec isn't enabled. This was a tiny change. It was 2 lines of code, not 10. 3 lines.
In and out.
It's only 2 if statements. Oh, the other lines had to be re-indented.
Yeah.
So yeah, it's a 4-line diff, whatever. That gives us 5% more forwarding performance, basically for free, without much effort. I wish I would find them now like that. There was this stealth firewall issue. Years ago, one of the idiots believing in stealth firewalls, invisible, for sure, found a way to detect an OpenBSD bridge running PF being configured in a stupid way. He sends a packet with corrupt protocol checksum. The end host would see that the checksum is corrupt or doesn't match, would just drop the packet silently. PF, if told to filter that packet and especially told to send an RST or an ICMP error back, won't reply because it doesn't even look at the checksum. But well, you have to configure it that way, and if you want a transparent bridge, doing that is kind of stupid. Anyway, well, transparent stealth bridges are kind of stupid anyway, so whatever. But with PF sending that RST or ICMP back was suddenly not invisible anymore, you could prove that it's there. The solution that we had in the tree for ages was to check the protocol checksum for each and every forwarded packet, as long as it was handled by PF. This is ridiculously expensive, but well, we had that in the tree for years. The fix, we just check the protocol checksum if we are about to send a reply back, and if it's corrupt, just don't send a reply back. So it only actually matters for the packets where we are going to reply, which is a tiny fraction. So the regular forwarded packet is not affected at all. This gives 7% speed up roundabout. Getting the current time is astoundingly expensive in some cases, especially on i386 machines with just the very old timing chip. We used the timestamp pool items when we were returning them to the pool. And yeah, well, that was just not necessary. I think Techie did that. Techie removed it. That gave, I don't have the exact numbers for that, but that was a big boost, like 2-digit %. Another change we did at the Slackathon in 2007, we used to stir the kernel random pool. This is where all the random numbers come from, once per packet. And well, stirring requires clock reading, so you're back at the getting the time is not cheap issue. And we now stir once per interrupt. And in one interrupt, you usually handle multiple packets, so that gave another very nice speed. That was a massive improvement. Didn't matter that either, actually. Since we traveled, you know we call PF twice. Once inbound, once outbound, always assuming forwarded packets. PF needs to remember some stuff in between those two invocations, or at least it's nice if it does. We need the queue ID so that all queue can select the right queue on the outbound side. We have the tag in the sense of the tag keyword in PF, so you can tag a packet on the inbound side and refer to the tag on the outbound side. For example, you can use that to express trust relationships between interfaces. We need the routing table ID for the multiple routing tables. Multiple routing tables is an anti-separate talk. We need loop prevention for PF route 2, which sucks anyway. And some magic for ECN and some other flags for various other things. So, that information used to sit in mbuf tags, which means I have to explain mbuf tags. So, when you travel, you give up your luggage. Sometimes you get it back when you arrive. The airline attaches a label to your luggage so that you can identify it and hopefully get the right way to the airport you're flying to and not to Heathrow. And this is exactly what an mbuf tag is. It's just a tag put on the outside of an mbuf, basically. The packet header has a queue head that points to, well, the queue head points to the members. The mbuf tags form a tail queue, and an mbuf tag is just a struct with the list pointer magic and the ID of the tag and the length, followed by the data itself. I changed something here, but future talk. The problem with that being is the memory the mbuf tags sit in has to come from somewhere. We used to use good old kernel malloc, and malloc internally is not exactly simple. We know a lot about memory management here, so you can imagine. This turned out to be a massive performance bottleneck. Don't try that optimization in your code. This is an exceptional case, and if you're trying to bypass malloc to be faster, you're being stupid. Many people tried that, and eventually they all failed. So don't do it. If you think that's your problem, you're doing something wrong.
So what are you doing?
Something wrong. But very effective, as you will see on the next slide. Oh, you don't. Actually, this change doubled performance. So it was massive. I'm telling this too early because now I'm telling the solution. Anyway, the solution was not to use mbuf tags, but put the stuff that PF needs directly into the packet header. Before actually doing that, I removed some of the stuff that we put in there in a cache style because it's actually cheaper to recalculate than to access the memory. This means that we don't have to malloc because it sits right in the mbuf. It also means that we are wasting a little bit of memory if you're not using PF, which doesn't matter because it's the mbuf and the data is usually sitting in the cluster anyway, and those few bytes don't really make a difference. Or they are well invested, let's put it that way. And the stuff that we put in the packet header, you see here, it's it's the pointer to the header, it's the routing table ID, it's the queue ID, the tag in the tag and tag keyword sense, it's flag field, and counter. The routed is a counter for route to do protection. Consequences. This is what I unfortunately told you too early. They tested up with the Dogsville Circus, which has really sucky nicks, running as a bridge, because then there's no queue involved, it's perfect for benchmarking. Pass as the only rule, and a single TCP connection through it. Before it was able to do 28 megabits, afterwards 56. Very nice.
And we found out further this week just how sucky those nicks really are.
Holy shit.
I
So,
found that out this week. It took you so long.
we kind of knew.
But it was just more horror.
If I was like you, I had been screaming all day.
Yeah.
It's been screaming all week.
Exactly.
Yeah.
But it has a nice side effect. If you want to learn about V-nodes, you go to the psychological department of this university. Yup. Our hack room was just right next to their building. They know everything about V-nodes now.
And angst.
It's true.
Did
So,
the same thing.
But
I did the same thing.
I'm surprised I hear that. I say that, but I can't hear you.
Never mind.
So, that's it, unfortunately pretty much with low-hanging fruit. Well, there might be some more, but I didn't find it yet. Well, other fruit is very yummy too, but that requires more work to get to it. Namely, we get to a phase where we have to do redesigns instead of little tiny code changes. First victim of that is the PF state table, which means I have to explain it now. PF is stateful. I just learned that from DLG. It tracks connections, right? It's kind of obvious for TCP because it's connection-based anyways, and for the other stuff, you just fake state by looking at the ports and the addresses involved and some timing magic and so on. Stateful filtering is wanted for security reasons, because we can do a much better job of matching packets to it. Oh, you already explained that. It's also much faster. So compare that routed traversal and an Atlantic travels like a boat, while the state table lookup is like taking the airplane. Network address translation and the interface-bound states unfortunately complicate things quite a bit because, well, obviously net changes addresses, and the interface-bound states take precedence over the floating ones. Our state table used to be pretty flat. Each entry had 3 addresses assigned to account for NAT, and this is also the reason why it was never possible, well, this was one reason why it was never possible to do NAT inbound or redirect outbound, because you only have 3 addresses, so you can only change one, not both. There was one global table, one global PF state table, and there was one PF state table per interface. And the interface, the one on the interface, always had to be searched before the global ones because the interface-bound states were in that one. So no way halfway saying uses interface-bound states, and still you had to do all the lookups in there. This was pretty expensive. So first step in changing that, we split the state and the state key. So the state's pretty big. The state key are the fields that are used for the lookup. So product, address family, addresses, protocol, ports if appropriate. I think that's it. Yep. Each state key has a queue of states, and each state points back to its state key. So first incarnation of the rewrite, you see the state key, which is pretty simple, points to the state items, which are separate items. In this setup, they could actually still be in the state. You'll see later why they can't in the long run. And each state that is in that queue points back to its state key. Now, since we now can have multiple states with the same addressing information in the table, each entry had to be unique, right? And now we have a queue. So you can have multiple entries. we don't need the extra state tables per interface anymore. As said, the colliding entries just hang in the queue. The interface-bound states are just always inserted at the very front of that queue, and the floating ones are always inserted at the tail, which ensures that our interface-bound states are always up front, the non-floating ones. And when we found our state key, we just traversed the queue of states, which is usually 1, and just check that the states interface pointer equals to the interface that we are on, or the state doesn't have an interface pointer. That gave a fair performance boost, but since that was at a hackathon and we did lots of other interesting stuff, I didn't actually measure it, which is kind of sad. So, next hackathon, Japan. We got a new state table logic. One thing that always annoyed Ryan and me big time was that triple address thing, because they were named weird and we could never remember what address was what and what got changed in what condition or whatever. It was horrid. So our new state key just has 2 addresses, source and destination, and since source and destination is kind of iffy in that case because they're exactly swapped when we handle the return traffic, we just call them address 1 and 2. And same thing for ports. And now each state has 2 state key pointers. One points to the state key as seen on the wire side that has the addresses as the packet on the wire. And the other points to what we call the stack side, which are the addresses, which has the addresses after PF is downloaded and potentially rewrote 1 or 2 of them. For this scheme to work out, the addresses on the stack side have to be swapped so that we can match return traffic. If that is a machine running OpenBSD, it actually is. You see the packet coming in to IP input, goes right into PF, PF does magic, and then it's sent out again. And the wire side is just before the call to PF, but the stack side is after, right? Same thing on the output side. So, looking at the new state keys, the easy and same case, without involving any address rewriting, we have the state key that has the queue with the 1 state, and both state key pointers in the actual state point back to the same state key. If NAT is involved, we have 2 state keys because obviously the addresses are different. So this is why we need to separate state item structs, because now the 1 state is member in 2 queues, and the actual state has the wire side pointer back to its wire side state key, and the stack side pointer back to the stack side state key. As I already mentioned, for this to work out, state operations like searching, insertion, and deletion on the stack side have to be done with the addresses exactly reversed opposed to the wire side. The reason being return traffic. Working that out was horrid. Many brains were twisted, and since we were in Japan, we had lots of sake and shochu to recover from that. Worked kind of well. And for the moment, please just believe me that this scheme is alright. If you want to understand it, I suggest taking a whiteboard and just write it down and draw it. This is what we did. This is our one.
Yeah, you're just right. Look up stack side is always reversed, and then you understand it.
Very important.
Yes, I did.
But
No, I just had it. You write in capital letters. Look up stack side always reversed, and then you understand.
Yep.
Yeah.
This is so big because it took us hours to figure out. So, now we have that. Now it's time to form relationships. Spooling. By definition, for forward connection, the stack side state key on the inbound side has to be the exact opposite as in address is swapped on the outside, on the outer interface. Exception, any form of tunneling, encapsulation, and so on, which is kind of easy to handle. Well, I underestimated that it wasn't that simple, but well, we made it. So we can form a relationship between those two state keys. Basically, the inbound one pointing to the outbound one and the other way around. Which then, on the outbound side, means we don't actually have to search for a state, but can just dereference the pointer. It's not that trivial, but yeah, anyway. So, next thing again, you have the two state keys that basically just get an extra pointer called reverse and point to each other. Rest remains unchanged. So, back to mbufs. You remember the packet header where we stuffed the PF information in, and we now just extend that by a pointer to the state key that we used on the inbound side, because we somehow find it out on the outbound side, right? Which on the outbound side makes finding the state trivial. Of course, all we have to do is follow the pointer. And, well, this is the code that only looks as hard as it is because we have to do all the casting. No more state table searches, and so everything worked, and I happily benchmarked, and that was very frustrating. It was only 10% faster, and I expected much, much, much more. So, frustration, Viking helps. Then taking this overview on the results, 10% is not all that bad, and this is foundation for lots of cool stuff that we can do later, so our optimism comes into play. The state key linking gives us a notion of flows in the kernel, because now we have something that describes, for example, a TCP connection, right? And you have many subsystems in the kernel that work based on these connections and that do keep some form of state on their own, like the TCP and UDP stacks.
Does this mean we can compete with Cisco and demand money per connection?
Yes.
The business plan.
But I have one.
If goldentshirt.com fails,
And the tunnelbana.
and we figured he can make more money sitting in the tunnelbana singing than he makes in Iceland. So, other subsystems do not keep state, but they could actually profit from doing so. First thing we did is invading the TCP and UDP stacks. Of course we invade.
German after all.
Pardon?
You're a German after all.
Supposedly. So, obviously, TCP and UDP have to keep state track their connections. So they use protocol control blocks called PCBs or prefix to the address family in PCB. IPv6 doesn't exist. And then you just use the PF state key that we easily find by following the pointer from the mbuf header and put a pointer to the PCB in there, which is the yellow line down here. Oh, I'm standing in front of it. So just add that. Before we are actually searching for a PCB, we just check the state key and check if the pointer is there. If it's there, you just use it. This is live code. This is all the changes that were needed. Follow the pointer. If it's there, use it. When we did search, because we had to, because the pointer wasn't set, we just set that pointer, and we actually established the connection in the other direction as well. So we have the INP pointing to the PF state, and we have the PF state pointing to the protocol control block. What's not shown here is when one of them goes away, either the state or the PCB, you of course have to break the linkage, of course, otherwise we just have crap pointers. Another subsystem that does not keep state right now is the routing codes. It could profit a lot. Routing tables are pretty damn big these days on BGP routers. Actually, the number is already outdated. On my core BGP routers, I have now almost 300,000 routes. So being able to skip a few lookups is very worthwhile. When we store the pointer to the route that we use for that connection in the state key, we don't need to do any lookups except for the first one, kinda. And that should help a lot. There's just a tiny little problem. Routes change. It's actually not a problem, but they can go away, or more specifics can be added. You can do it. Solution to the routes going away, they simply must not go away. It's actually easy since they are already ref counted. Basically, when it's supposed to be removed, it's flagged invalid. Actually, it's the other way around. The valid flag is taken away, removed from the table, but still exists, so pointers to it are still valid. If you try to use a route from a state key and it's flagged invalid, we just do a new lookup. And the red point, of course, which has that problem solved and leaves us the more specific problem that I need to tell you to solve. So, assume the destination for our connection is 10.0.0.1, and the route lookup gave us the default route. We link the default route, and, well, use it. So, now somebody adds a route to 10/24. If we do a new lookup, of course we get 10/24, because that's the best match. But since we have the default route linked from the PF state key, and the default route is still valid, we would continue to use it, which is wrong. Olga insisted on the dragon. The solution has dragons in it because it involves route.c. So before inserting, route.c makes NFS looks good. Before inserting a new route, you have to do a route lookup, or basically you can do that while you're inserting. Find the less specific one if it exists. If so, remove it, mark it invalid, make a copy of it that is still not good, and reinsert that one. And the state key still points to that route, but this is the copy that we removed. So you notice it is now being invalid. We do a new lookup and find the right route. On to something different. But
At least that's your idea behind it.
it works. I implemented everything except for the more specific problem yesterday or the day before. It works. The more specifics aren't being added anyway. So, on to something different. PF has this wonderful TCP connection tracker that looks at the TCP flags and forward the state of the PF state according to those flags, like established or time wait and all that stuff. The other thing it does, it verifies the sequence numbers against the window. Details learned from DLG's talk. As we also learned from DLG, that cannot work when your machine only sees half of the connection, as in A to B this way, B to A this way. And well, problem being, as DLG said, PF doesn't see the window size announcements, at least not all of them. So I implemented a sloppy state tracker that does the bare minimum. Oh, the reason why I want stateful on routers that are not on the edge, there's no guarantee that there's symmetry in routing. So you really have to deal with asymmetric routing, which automatically leads to that case. So I implemented a sloppy tracker that does the bare minimum. It's just looking at the TCP flags, nothing else. It doesn't even bother to touch the sequence number. This tracker is dangerous. Don't use it because you think it's faster or something. It is only to be used in these very special circumstances where you deal with asymmetric routing. With not using the full-blown tracker, you give up one of PF's strongest strengths. This is really what makes PF very different from everything else.
You should
So-
have just named it IP tables, then everybody would know.
Yep. Since the full-blown tracker does much more work than the sloppy one, I mean, just look at the lines of code. It's 326 for the full-blown, and the sloppy one is just 69. I expected the sloppy one to actually be faster. Except you don't really want to use it on your firewall, but it's okay for forwarded connections to only do the sequence number check on one side, right? The second check on the other side will not make a difference. So the term auto-sloppy came up. Of course, we can just use our state key linking for that. When we have the state key, we get to the other key and we know it has been forwarded, and the state key is there means it has been checked already, right? So by the time we establish the linking, I just mark one of the two states as sloppy, and yeah, well, as the other will do the sequence number magic. And yeah, benchmark time, frustration is slower. You know why?
By how much?
I don't remember. You'll see, but this is irrelevant. So to better understand what's going on, I benched the sloppy tracker on both sides versus the full-blown one on both sides. And to me, surprisingly, there was no difference at all. So why is the sloppy tracker, which does so much less, not faster. The limiting factor are not the CPU cycles. The limiting factor is memory access. So then the sloppy tracker waits for the memory, the full-blown one just does the TCP sequence number check, which essentially is thus free.
Like memory access, you mean cache, basically, your backup.
That's your area. I just take the limited, simplified view. Sloppy performance lessons. Why is the full-blown one on one side and sloppy on the other? Well, we just found out the sloppy and the full-blown one are as fast as each other. So why is using one on one side and the other on the other side slower, not just as fast? So the theory is that we are trashing the instruction cache too often, which also tells us another lesson: petrol-sized code helps. And needless to say, my auto-sloppy code went directly to the nut. That's it pretty much. Of course, we didn't stop hacking. There were a few hackathons afterwards that I'll maybe talking about in the future. There was N2K9 in Basel very early this year. There I did the massive changes to Scrub that are actually in the tree, and our dear Paul Thoman could not be there because unfortunately he died in 2005. Then we had C2K9 in Edmonton, another network hackathon. Oh, some people did something else. It's a network hackathon. There I basically rewrote the PF network address translation code. It's a massive diff. It will probably go next week. You'll think it's insane, but it works. No bugs. Everything else is propaganda. And we have this wonderful hackathon here. Yeah, judging from the picture, you can see where I was into. It's like the output. I did various little things, but I don't want to talk about it. That's it pretty much. Questions? No questions.
I have one. It's kind of silly, but since rule set lookups are so slow, if you like separate the rules into like anchors with filters, will that do anything at all if you have a lot of rules? No. Okay.
Actually,
It will help. If you can split.
having the rules in the right order helps,
Yeah.
but I kind of doubt you'll be able to find out what order is right, because for that you have to know the inner workings of the skip steps optimizer.
Yeah.
Splitting into anchors helps if you make sure that the giant rule block inside the anchor only gets executed if some condition on the anchor itself gets it. So you could do anchor to port 80 and then inside the anchor do whatever HTTP stuff. That could help. I'm not sure. I've never tried it.
It's not a problem.
Especially
I have
when
just
you're fighting against skip step optimization.
Exactly.
How many actions are you creating versus pushing? I mean, you're going to do thousands and thousands of packets for existing connections. You
Well,
create hundreds.
Unfortunately, the rule set traversal is the attack case, right? Where we block everything. This is really sad, but what should we do? That's it.
Block states.
Yeah, we tried that, but we thought about it. I still don't really see how we can do it in the same way.
Why do you need to give those ugly casts?
Because because we don't want mbuf.h to include pfr.h. Could do extras. Yeah,
Well, you can do it just in order.
that's true. Why didn't I do that? And okay for an unwritten div. Interesting.
It's only 3 lines.
So what is your speed record through PF with all the new
I don't know.
improvements in packets per second?
You're asking?
Yeah, I'm asking
No,
you.
sorry. You're asking for the absolute limit?
No, I mean,
What's
what's
the
your
fastest
speed
you see?
record? What's the highest number of packets per second you've seen through PF?
You can't tell. Depends on the traffic. Depends
Yeah, I
on
mean,
the
what
hardware.
have you
Depends on
seen
the face
in
of
lab
the route.
environments and whatever?
I don't know.
The
Maybe
interface
million.
depends upon the interrupt
Right.
subsystem, depends upon everything.
Yeah, but I
Absolute
mean,
maximum doesn't actually mean much.
Just make sure that your hardware is fast enough.
Yeah.
Alright.
Just
For
quite
what
fast
you're
hardware.
using.
so we'll see
One
wire rate 10
one
gig
single
next
fast
week
core.
or
For now, one single fast core.
How fast is fast enough.
Just buy the fastest you can get. It costs nothing anyway.
And it will get better. Step by step.
Yep. Beer in Stockholm is more
Talk about the
expensive.
We got like 5.
Oh, right. Theo did a tiny little, it was you, right?
Yeah.
Tiny little fix to the Mbuf handling. Basically misplaced not misplaced, but unclever placed SPL and SPLX.
Yep.
And yeah, wow, that's a 30% performance improvement
In your tests.
in my tests. Just forwarding packets.
And that's on the crappy server.
That's on the crappy servers.
Yeah, how many packets are you forwarding on that thing then? You have PF on, right?
Yeah.
It's like 25,000.
Yeah. 2,500, 3,000. Not much. Circle sucks in many regards.
But that's why it's impressive.
Just that single state is IPv4 and nothing else.
My test setup is one small box surrounded by 2 fast boxes. The 2 fast boxes run TCP bench. This time I used 50 connections. Of course now I can. And the box in between, depending on what I want to bench, this time I was working the IP stack, so it would be pointless to make the box a bridge. Because then the IP stack doesn't get involved. So it was packet forwarding, it had TF on, and just a single pass-through. Well, actually it had the default rule set, which comes close to that.
So you're actually not quite sure if you add on a lot of IP stack and stuff, if it actually
Nope.
slow up.
No, I don't know. But I can make an educated guess, doesn't change a thing.
It's just a couple of if statements.
You did educated guessing on the sloppy thing and it turned out to be slower anyway, so.
That was not, that was just guessing. That's it.
One last question.